Welcome everyone to the 37th meeting of New Directions in Group Theory and Triangulated Categories. Hope you all had a great Easter. Today our speaker is Neil Strickland from the University of Sheffield, and he'll be speaking to us about questions around the chromatic splitting conjecture.
Okay, thank you. Thanks very much for the invitation, and thank you everyone for coming. Nice to see everyone. So I thought I'd talk a little bit today about the chromatic splitting conjecture. As in the title, I've got more questions than answers, but I think there's some quite interesting questions here, so I hope you'll enjoy it. And so what's chromatic splitting conjecture about? So this is a conjecture due to Mike Hopkins about the structure of this thing, which I'm going to call alpha n of S, which is, so we take the sphere spectrum, we localize with respect to Morava K-theory, the Kn, and then we localize with respect to En minus 1. So a little technical note here. Turns out I'm going to take S to be the p-complete sphere spectrum. And then everything, almost, when I talk about spectra, what I really mean is modules over the p-complete sphere spectrum. That turns out to be the right ground category to use. So that's kind of intermediate between, of course, p-local spectra and p-complete spectra. We do include things like the rationalization of the p-complete spectrum, which is the kind of the Moore spectrum for the p-adic rationals. That's not p-complete, but it is a module over the p-complete sphere. And so if I write anything like mu, then really I mean the p-complete mu. So a bit more notation. SND is going to mean the En localization of the D sphere, and SN hat D is the Kn localization of the D sphere. I'm going to do this kind of thing with exterior algebras. Okay, so I've got a ring spectrum R. So this is going to be in the most naive kind of category of ring spectra. Mostly I'm going to work in just you look at the category of spectra, and then objects with a purely homotopical multiplication that's associative and commutative up to homotopy. And so we've got this kind of exterior things, whereas we've got some variables Zi, and each variable has a declared degree and a declared height. So we've got some variables Zi, a degree Di, which is always going to be odd, and a chromatic height Ni for each variable. And then what I mean by the exterior algebra, we take our ground ring R and then we smash it with these kind of single variable exterior algebras where you have the zero sphere and then the Di sphere, but localized with respect to Eni. Okay, so that's what I mean by this sort of chromatic exterior algebra. And of course, here you've got a smash product of a bunch of factors. You've got n factors, each of which is 2 summands. So you expand it all out, you get 2 to the n terms. And when you expand it out, the thing to remember is that you smash 2 of these localized spheres together. Of course, the degrees just add, but the chromatic height gets minimized, right? If you do, you've got a sort of an L3 thing smashed with an L5 thing, that's just an L3 thing again. Okay, so when we smash this out, you expand out this smash product here, we get a whole bunch of localized spheres of different chromaticity and different dimension, and then we smash it. Okay, so we're going to have a whole bunch of variables which are going to be called xin, and xin is, and these are where I is greater than or equal to 0 and strictly less than n, and these have got height I, and the degree is 1 minus 2 n minus I, so that's odd and negative. So the chromatic splitting conjecture says that these xni INs, they can be interpreted as maps from the sphere, the localized sphere of height I and this dimension, mapping to this spectrum alpha ns, which are up here, the ln minus 1 lkns. So we can interpret these xins in that context, and then they give rise to a map from this exterior algebra here to alpha ns, and then the conjecture says that this map should be an equivalence. So of course it's so it's highly non-obvious that maps xin like this should exist, but that's the conjecture. And just an example, let's look at alpha 3s. So that's E2 localization of the K3 localization of the sphere. And so you've got your ground ring here is S2. And then your various exterior factors, you've got an S0 minus 5, that's a rational sphere. S1 minus 3, that's like a K-local sphere. S2 minus 1, you smash all those together, and expanding them out according to this rule that we've written here, you get 8 terms localized spheres with various different heights. There are 2s2s, 2s1s, and 4s0s, and that's how it goes. And in dimension varying from 0 here to -9 for the last factor. Okay, so so where does this conjecture come from? And a couple of things that sort of provide orientation. First one is this thing about the cohomology of the Morava stabilizer group. So gamma n is going to be a fully extended Morava stabilizer group. This is the version which incorporates a Galois group, and it acts purely by the Galois thing on the width vectors of fp to the n. And you can look at the cohomology of that. And that's known to be exterior algebra on generators, which we could call xin in these dimensions here. So these kind of match up with the xins that I have in the previous page. And so, yeah, so we've got this this Carbology Isomorphism here, which was already in Jack's original paper about these kinds of things. And if you call why this is, I mean, it's basically your gamma n is a Galois twist of the general linear group, or at least the Lie algebra for gamma n you can interpret as a Galois twist of the Lie algebra for just the general linear group. And then there's a kind of well understood theory about the cohomology of the general linear Lie algebra, and the Galois twisting turned out not to make much difference. So so we end up with this. Okay. And so, so how should this be related? I mean, you've got the, you could look at you've got Adams type spectral sequence for the homotopy groups of the Kn local sphere. So the E2 term of that is the cohomology of gamma n, not with respect to this width ring, but with respect to this kind of much larger ring, the pi 0 of the Morava E-theory. And then you've got this spectral sequence, and then you could rationalize all that. And so the hope is that once you've rationalized, it doesn't actually make a difference that there's all this extra stuff, the whole homotopy of the Morava E-theory. And so the hope is that you're just kind of left with these xins. And then that would tell you about pi 0 of that would tell you about the E0 localization of the Kn local sphere. And on the previous page, we didn't have the En localization, we didn't have the E0 localization, we had the En-1 localization. So that's a kind of rather more delicate thing, but nonetheless, here there's a kind of a obvious way that these things can try and match up. And the other thing that we can say about the generator, so there is a known map here, known map called zeta, which goes from S-1 to the Kn local sphere. Yeah, I mean, that's you've got this gamma n here, and there's this determinant map going to the p-adic units, and one sort of take on the atom spectral sequence is that if you take your Morava E-theory and the homotopy fixed points of the full gamma n, then what you get is just the Kn local sphere. And if you take fixed points with respect to not the whole gamma n, but just with respect to the kernel of this determinant, then you get this thing, this spectrum, let's call it R for the time being. And the point about R is that it's kind of rather analogous to p-adic K-theory. This R, you've taken away the action of the kernel of this determinant, but you're left over with an action of the p-adic units, which is kind of like the Adams operation action of the p-adic units on K-theory. And there's a whole bunch of analogies between this R that you get and p-adic K-theory. A bunch of different people have written different stuff about that. And personally, I'm kind of a big fan of Craig Westerland's treatment of this kind of question, which sort of emphasizes how this R is kind of quite similar to K-theory. But anyway, so then you can still do like the K1 local sphere, the sphere that's local with respect to p-adic K-theory. You can interpret that as a fiber of psi k minus 1 acting on K-theory, and you can interpret the Kn local sphere as a fiber of psi k minus 1 acting on this thing that I was calling R, and from that it's easy to produce this zeta. Okay, So that's what I'm going to say about the generators. And then, so we've got these various localization functors, the LNs and the LKNs. So let me just kind of review a few things about what happens when you compose these. So these are kind of basic, well-known things about what happens when you compose some localizations. First one that I've kind of more or less mentioned already, if you do two of these EM localizations, you do LN and LM, that's the same as doing the minimum of them. And then if you, then as I said, the chromatic splitting conjecture is about what if you do KN localization first and then EN localization, or EN minus 1 localization. If you do them the other way around, then there's no mystery. You do LKN, LM. It's either LKN if n is smaller, is less than or equal, or 0 if n is bigger. You do LN, LKM. Okay, so the question mark, this is in the region that the chromatic splitting conjecture is about. Well, that's when n is less than m, n is bigger than m, greater than or equal to m, then it's just the same as LKM. And similarly, if you do LKN, LKM, in n less than m, that's kind of similar to this one. That's kind of in the world that the chromatic splitting conjecture is talking about. N and m are the same, you just get LKN again, and n is bigger, then you just get 0. So those are all basic relations. So as I said, we've got these kind of variables xin, and it's convenient to sort of draw these in a chart like I've got here. Okay. So down here I've got the dimensions. Say dimensions are always odd and negative, so you get all these, say, put them in a table, the odd negative numbers down here. The horizontal coordinate is the height. Okay, so xin has height I, and I say xin I'm saying has target n. In other words, it kind of maps to this alpha n thing that we're looking at. So so all the things with the same target are written as a diagonal stripe here. Okay, these guys down here, these are all stuff that maps to alpha 5s, stuff that maps to alpha 6s, alpha 7s, and so on. Okay, so we're saying the chromatic splitting conjecture says that if you look at alpha ns, that's exterior over the n-1 local sphere on these generators, which are arranged in one of these diagonal stripes. Okay. So here, in particular, alpha 4s, you've got your x0, 4, x1, 4, x2, 4, x3, 4 in this stripe. And then there's your alpha 6s, and most of the time I'm not going to write the names of the variables. It's kind of easier to see what's going on if you just put blobs everywhere. So yeah, so alpha 6s, so in this stripe with a 6 at the top, you've got these 6 generators. And there's alpha 9s the same way. Now let's look at alpha 469. Okay, so by alpha 469, I mean the composite kind of in increasing order like this. So you've got alpha 4 composed with alpha 6 composed with alpha 9. Okay, so remember, so alpha 4 is L3 LK4, alpha 6 is L5 LK6. So in this kind of gap here, there's implicitly an L5. But if you look back to the kind of relations that I said between localizations, LK4 composed with L5 is just the same thing as LK4. So it doesn't matter whether I put the L5 in there or not. And similarly, there's kind of implicitly an L8 here, and that doesn't matter either because it just gets wiped out by the LK6. But all these things that these are you've got these functors alpha n, and in each case there's a natural transformation from the identity to alpha n. And because of that, you've got your alpha 4, your alpha 6, and alpha 9. They all map to alpha 469 like this. Okay. And so you've got all this stuff in this stripe here. These are all the generators for alpha 4 of the sphere. And in this stripe, you've got all the generators for alpha 6 of the sphere. And in this stripe, you've got all the generators for alpha 9 of the sphere. Okay, but it turns out that some of these generators are actually 0 in this context. That's kind of pretty easy again to see from these relations between different localization functors, which I mentioned earlier. So which ones are 0? The ones that are 0 are the ones that are shadowed. Okay, so here you've got all these guys here, but they're in the shadow of this stripe that you had up there. Okay, so all these And then you've got a couple more here that are shadowed by these here, lying directly below it. And so all the shadowed things, they become 0. And so we just end up with these dots that are marked in black. And so if you think about it, that means that the number of generators is always the same. If the last alpha that we use is alpha 9, then you're going to always end up with 9 generators. So you get, but depending on what you put before the alpha 9, the degrees of the generators are going to be different. And so as a kind of extreme example you can think about, we could do alpha 1, alpha 2. Well, you could do the composite of all the alphas from 1 up to 9. And as I said before, that's kind of the same as you've got there's implicitly an L0 in here and then an L2 there, but they all get wiped out. And also remember, LK0 is the same as L0 for the zeroth localization. It doesn't matter whether you use K0 or E0 because they're the same. So alpha 1 up to 9 is just the same thing as this composite of all the Morava K-theory localizations. And the kind of conclusion from the story that I said before is that this guy here is exterior over the rational sphere on these generators here that are marked with black blobs. Those are x01, x12, all the way up to x89. All the things of the form xn-1, n. These all have to go, they're all in the top row here, the dimension being -1.
Excuse me, Neil, why are there 10 functors up at in alpha 1 through 9? On the right, you have a composite of 10 functors rather than 9.
Oh, yeah, okay. Well, right. So here, LK0, LK1 is alpha 1, right? Alpha 1 is L0, LK1.
But in your previous example, you had 4, 6, 9, and it was a composite of just 3 functors.
Okay, well, it was a composite of 3 alphas.
Oh, I see.
And it's a composite of 4.
Oh, okay. All right. Got it.
Yeah.
Thank you.
Yeah. So it would kind of match up better if I'd written L0 instead of LK0 here. But L0 and LK0 are the same. Yeah, and to be clear about the status of these things, okay, so obviously I'm assuming chromatic splitting conjecture, but if which is about the status of kind of a single alpha n, but if you assume the chromatic splitting conjecture, then you can deduce all these other things that I've said. So we might be interested in something a little bit different. We could look at LK4, LK6, LK9. Okay, so here I'm going to call this phi, where I just do composite of these L's. And think about it a little bit using the relation between localizations that I said. This composite here is the same thing as LK4 composed with alpha 6 composed with alpha 9. Okay, so I could do it either as a composite of 1 K-theory localization and 2 alphas, or just a composite of 3 K-theory localizations. So we'd like to see how this one works out. So what have you got? Well, so like I say, because from this description here, you can see that alpha 6, 9 maps in. Because you've got an LK4 on the outside, the K4 local sphere also maps in. So if we did alpha 6, 9, then according to the prescription that I had in the previous slide, you've got stuff in this stripe here and stuff in this stripe here, and all these guys in this stripe, they would get shadowed, but these ones wouldn't be shadowed if we look in alpha 6, 9. But putting in the LK4, that's kind of, I put in these kind of squares here. So the squares correspond to variables that aren't actually there, but they still have the same shadowing effect as if they were there, if you like. The kind of effect of putting this LK4 here is to shadow these extra variables here. So you're just left with the ones over to the right. So okay, so here's the claim again. So this is a thing that follows from the chromatic splitting conjecture, and as in a lot of things I'll say, I'm doing I'm doing a bunch of specific examples because if you don't do specific examples, then it's kind of easy to get kind of buried in a huge morass of notation. But all of these things kind of generalize in a fairly obvious way. So yeah, if we do this case here, so the claim is that 5469S is exterior over the K4 local sphere on these 5 generators that are marked in black. So again, and the kind of orange circles correspond to things that are sort of morally present that are equal to 0. But notice also, let me just kind of go back here. When we looked at alpha 3 of the sphere, then we've got a bunch of different spheres here. These are all EN localized spheres for various different N's. Some E2 local, some E1 local, some E0 local. And that's what you typically get with these alpha N spectra, or composites of alpha N spectra is the same. If we were to kind of expand all this out, you get a bunch of products. I mean, like this. So this generator on its own is local. So this generator on its own, say, is E6 local. But when you multiply anything by this one, this one is E0 local. So anything you multiply by this is also E0 local. So yeah, you get a bunch of different spheres of chromatic heights between 0 and 8. But if we do instead do this kind of thing here, where we're just composing Morava K-theory localizations, then you always end up with all the terms you get when you expand it out. They're all Kn local spheres for the same N, which is kind of the initial, the kind of initial Kn localization that you put in there. Okay, so that's all kind of follows from the chromatic splitting conjecture, but you can ask sort of whether the chromatic splitting conjecture is actually true or not. That would be nice to know. But I should mention, of course, the chromatic splitting conjecture, this is known for n equals 1. It's known actually to be false for n equals p equals 2. That was proved by Agnes Beaudry. She did enough calculation of homotopy groups to show that the chromatic splitting conjecture can't be true when n equals p equals 2. But we can still hope that it's true when prime p is large relative to n, and even when p is small relative to n, we can still hope that somehow the chromatic splitting conjecture is capturing some part of the truth, that it's kind of true up to sort of filtration with mild attaching maps in some sense. But so yeah, we can still hope that it's telling us something. But there's a kind of key test that you could think about here. It's known that there are these chromatic fracture squares, or chromatic fracture hypercubes. So I've written down the one for L2. This is a L2. We've got a cube. For Ln in general, you get a kind of thing of dimension 2 to the n plus 1. And so you've got a kind of hypercubical diagram like this. And all the terms are kind of these phi's. So remember, we had the phi here. Phi 469 is LK4, LK6, LK9. Phi 01 is LK0, LK1, and so on. And this is a homotopy Cartesian. And the homotopy Cartesian means, well, one way to say it is that you take the map from this top left vertex to the homotopy inverse limit of the rest of the diagram. Then that's an equivalence. Or another way to say it is the total fiber of the cube is 0. So this fact, I think, it was certainly known to Bousfield a very long time ago, being written up by various different people in various different kind of technical contexts. Infinity categorical version, I'm afraid I'm not remembering who wrote that one up. I should check that. But yeah, anyway, there are earlier versions that kind of are the context. Okay, so so the total fiber of the cube is 0. So explain what total fiber means. Well, total fiber is a concept that's that you get for a kind of n-dimensional hypercubical diagram. So for a one-dimensional thing, that's just like a single morphism. Then the total fiber is just a fiber. Total fiber of a square. Okay, you take a fiber of one edge, fiber of the other edge, and it's the fiber of the map between those. Total fiber of a cube, you take total fiber of one face, total fiber of the other face, and the fiber of the map from one to the other. That's the total fiber of the cube. Of course, it's not super clear that that's well defined, because when I do this thing with a square, I can do this edge and this edge, or I can do the top edge and the bottom edge, and it's not clear that you get the same answer both ways. But there is a kind of more symmetrical way of saying what the thing is, which makes it kind of clear. Okay. So the claim is total fiber of this cube is true. And so that means you get a kind of you can get a spectral sequence. So what exactly did I say here? I mean, the kind of most obvious sort of thing that people would say is that there's always a spectral sequence for the homotopy groups, say, of a total fiber. So you get a spectral sequence which kind of involves all these phi things and then converges to the homotopy of L2. Actually, I want to advocate this point of view that it's better to leave in leave in the L2. Then there's a kind of slightly re-indexed type of spectral sequence which converges to 0. So instead of having a spectral sequence based on most of the diagram which converges to L2, you have a spectral sequence that's based on the whole diagram and which converges to 0. And various things are kind of tidier from that point of view. So the E1 term is like a product of the homotopy groups of everything everywhere in the cube and converges to 0. And this, if you can't understand what this is like, it's actually like the Morava spectral sequence. Suppose we've got a space X and some open subsets, U0, U1, U2, say. I'll just do the case of 3 subsets. And then you can look at all their intersections, like and you write U02 for U0 intersect U2 and so on. And from this you can build a Morava spectral sequence, and you can do a Morava spectral sequence that converges to the cohomology of X. But in the same way as I was kind of saying here, it's actually tidier if we make a spectral sequence where cohomology of X appears on the E2 page, E1 page even, and the whole thing converges to 0. So in the Morava situation, right, you can take your E0 page just to be the product of all the cochain complexes for the various intersections. And then the E1 page is the product of all the cohomology groups of all the various intersections. And a way that you can kind of organize that to sort of understand about the multiplicative structure is like this. We can make a exterior algebra on generators E0, E1, E2. And so you get a basis, EA will be the product of the EIs for I and A. And so you get the obvious kind of basis for the exterior algebra. And then this E0 thing here, you can kind of think about this CQ of UA as being tagged, being multiplied by this generator EA here. Okay, and then you can kind of think, I mean, this C upper star of UA is a quotient of C upper star of the whole space X. And so this whole thing here is kind of a quotient of the cohomology of X tensored with E. This has a kind of a bicomplex. It's got 2 orthogonal differentials. One of them is just the ordinary kind of simplicial codifferential on the cochains, which of course induces codifferentials on each C upper star UA. And then you've got this U, which is the sum of the generators of this exterior algebra. That multiplication by U, that's a differential in the orthogonal direction. This is a one-dimensional class of a square of 0. And then, so you do a combined differential, the usual sort of business for a double complex. You just might add the two differentials, connect that. And this the vertical differential is going to satisfy a Leibniz rule. The horizontal differential is multiplication by a constant, so that doesn't satisfy the Leibniz rule. So the combination is kind of not, it's not like a pure differential operator, which we're normally used to, which satisfies the Leibniz rule. It's kind of more like sort of operator where you differentiate and operator like f goes to f dash plus uf. And so this is kind of just a bit of an aside, but I think multiplicative properties of this kind of spectral sequence deserve some more attention. I mean, like I say, this spectral sequence converges to 0, and that's kind of quite a hard thing for a spectral sequence of rings to do, right? I mean, the spectral sequence of rings with a Leibniz type operator, then 1 will always be a permanent cycle, and then it's kind of often there's other constraints which prevent 1 from getting hit. But if you've got a differential of this type, then it can converge to 0. And also, I mean, here I've done this with kind of cover by 3 sets. You do cover with 2 sets, then it's a little exercise to see how this really is just exactly the same thing as the ordinary Major-Torus sequence. Okay, so one kind of compatibility between between chromatic splitting and the chromatic fracture square is like this. So here, so you come back here, we've got this is a square of functors which we can apply to any spectrum that we like. Okay, and so we can apply it if we want to the K3 local sphere, and then what you get is a homotopy Cartesian cube like this. Because I put the K3 local sphere, everything's got a 3 in it at the end. This is LK0 of the K3 local sphere, LK1 of the K3 local sphere, and so on. Okay. And so we've got this homotopy Cartesian cube as above, and the chromatic splitting conjecture, as I've discussed, it kind of gives us descriptions, conjectural descriptions of every vertex in this cube. And so it's of interest to ask, whether those that system of descriptions of these vertices is kind of consistent with the chromatic fracture thing, which says that this should be Cartesian. So let's kind of have a look at how that works. Okay. So here we've got this cube of spectra, and then here we've kind of got what the chromatic splitting conjecture says that those different spectra should look like. So there's kind of a bit of notation here. Remember up here, so this guy here, this was just, as we said here, this is just alpha 3. And as we said, alpha 3 is kind of it's supposed to be one of these spectral exterior algebras on 3 generators. 3 generators are x0, x03, x13, and x23. But I've left out the x's just to save space. So this is x03, this is x13, this is x23, and then some products, x03 times x23, x13 times x23, etc. So, and then empty is the empty product, which means the generator 1. Okay, so we've got these 8 generators here. And as we discussed previously, these are kind of correspond to spheres of different chromatic height. Okay, so these two here are rational spheres. These two here are E1 local spheres. Oh no, I said it the wrong way around. So these ones here are going to be E2 local spheres. These ones are E1 local spheres, and then these 4 over here, these are all rational spheres. Okay. So you get a bit kind of a mixture in this one here. But then these other ones over here, these are all phi's, and the phi's, remember, they all have they all give you spheres of the same type. Okay, this one is just phi1, phi3, which so that just gives you K1 local spheres. This one here is LK2, LK3, which just gives you 2 K2 local spheres. This one is LK1, LK2, LK3, which is again giving you K1 local spheres. On the right-hand side over here, everything is rational. These are all, each of these guys is consists of 8 rational spheres of different dimensions. So if chromatic splitting conjecture is true, then this ought to be a homotopy Cartesian cube. So can we see that it's homotopy Cartesian? Yeah, so we can divide this into sort of 3 parts. So here's a certain subpart where we've just taken out a bunch of the generators. Okay, so we've got a this is what we had by sort of taking the fracture cube for L2 and applying it to the K3 local sphere. But we can also just take the fracture cube for the E2 local sphere. That's kind of a simpler case. And what we find is that these kind of things that we've wrapped in blue here, that's just kind of 2 copies of the fracture cube for S2. So if we believe that the chromatic spinning conjecture is consistent with the fracture cube for S2, then it's also consistent with this part of the fracture cube for K3 local sphere. So yeah, modulo that, we can sort of take out this stuff because sort of saying that the total fiber of this part is trivial. So the total fiber of everything, we can ignore the bits that I put in boxes. Okay, so let's ignore that. So this is what we've got left. And if you go back here, you'll notice that everything on the bottom face is in a box. So we've lost the whole of the bottom face and some of the top face. Okay. And now we can take out another part here. So on the previous lot, this lot is all kind of copies of the fracture cube for S2. This lot is 2 copies of the fracture square for S1. Okay, so this part here again, we can sort of assume inductively is Cartesian. So we can discard that bit as well. And then what have we got left here? I mean, here, everything over here is rational spheres. These guys here, these were sort of mixed types of spheres, but now the ones that are left, these are all just rational. And so this is just basically the fact that L0 and LK0 are the same is saying that this map across here is an equivalence. So in other words, the fiber of this diagram is trivial. 4 copies of the fracture interval for S0. That's homotopy Cartesian. We discard those. And so now we get here, we see that our original diagram was homotopy Cartesian. So that's kind of that's kind of an interesting consistency check. But as I say, this is kind of saying that the chromatic fracture story for the K4 local sphere is consistent, provided that the fracture story just for the ordinary sphere is consistent. And in fact, more generally, by this kind of game, we could reduce everything to the case where we just look at the fracture square, fracture cube for the ordinary sphere. So that's what I said here. If you've got any of these kind of alpha A's where you do some composite of various different alphas, chromatic fracture hypercube for that is sum of chromatic hypercubes for various localized spheres. So this kind of reduces us to asking about whether this kind of diagram here, where we just look at the just got an E2 local sphere here, and we look at its various phi's. This is phi 0, phi 1, phi 2, phi 0, 1, phi 0, 2, phi 1, 2, phi 0, 1, 2, etc. This chromatic spinning conjecture implies that we should have a homotopy Cartesian cube like this. Okay, so is this true? You might think, well, we can just stare at this cube and ask ourselves whether it's homotopy Cartesian or not. But to do that, we need to know what the maps in the cube are. And of course, all the objects in this cube, we can all the objects are kind of nicely defined. We don't need any conjectures to define these objects. We do need the chromatic spinning conjecture to define some of the maps. Not all of them. I mean, this map here, this is just S0 hat mapping to an exterior algebra of S0 hat. That's just kind of the inclusion of constants. That's fine. Similarly, this one here, well, this is got exterior algebras over S0 hat. Your x12 is mapping to x12, x02 is mapping to 0. So this is kind of a perfectly well-behaved map that we know all about. But this map here, from the K1 local sphere to a wedge of two rational spheres, we only kind of know this exists if we believe in the chromatic spectrum conjecture. I mean, we know, of course, that there's a map from S1 hat to its rationalization, but we need the chromatic spectrum conjecture to identify that rationalization of this object here. So we don't really have this dotted arrow immediately, and similarly for some of these other solid ones. Solid ones, these are the ones that don't really change the coefficients. Okay, so everything on the right-hand side, the coefficient spectrum is S0 hat. Here and here, coefficient spectrum is S1 hat. So if you're not changing coefficient spectrum, then the map exists unconditionally. But the ones which can change the kind of coefficient spectrum, then we need the chromatic spectrum conjecture for them to exist. But on the other hand, we can filter everything in a reasonable way. So here, we do a sort of decreasing filtration on any of these kind of rings, where the sort of stuff of filtration at least one is sort of everything that's generated by these variables, and then stuff of filtration at least two is products of two variables, and so on. So we've got this kind of decreasing filtration, and it's not hard to see that if we assume the chromatic splitting conjecture, then then that gives us these dotted maps, and the dotted maps preserve this decreasing filtration. Okay. Okay, so that gives you a filtration of everything except for the S2. But then there's kind of a unique way to make a compatible filtration of S2, right? I mean, you take, for the stuff of filtration at most one, well, you take the filtration at most one everywhere else in the diagram, and you just take the homotopy inverse limit of that and declare that to be the second filtration of your S2. So you get your compatible filtration of S2. And so you'd like to know, what's the associated gradient of that filtration. Okay, so let's look at the zeroth part of the associated gradient. So in other words, that's kind of where we're modding out all the variables, if you like. Okay, so go back here, we've got these various exterior algebras, we're modding out the variables, so this just becomes an S0 hat, this becomes S0 hat, this becomes S0 hat, this becomes S1 hat. So we just end up with this. Okay, and so we want to know what should be what goes in here. So we're kind of declaring this to be the homotopy inverse limit of the rest of the diagram, which means that the total fiber has got to be trivial. Okay. And so how can we arrange for total fiber to be trivial? Well, total fiber of the right-hand face is already trivial because this is just constant. Okay. So we can kind of discard the right-hand face when thinking about total fiber. And then once we've discarded the right-hand face, well, this kind of front edge here, again, that's just the identity. So total fiber of that is trivial. And so in order to make total fiber trivial altogether, then total fiber of this edge has to be trivial, which means that the zeroth grading part has to be S2 hat. So that's what we've written here. Zeroth graded piece is going to be S2 hat. Now we're going to ask, what's the first graded piece? Okay, so here, first graded piece, you've got your generators, but no product of generators. And so these guys here, and here, we kind of go back a couple of things, here we just didn't have any variables here, or here. So we're going to get 0. Here we've got one variable, here we've got one variable there too, and there too. So this is what we end up with as the first graded piece. The first graded piece for S2 has to be arranged in such a way that this diagram is homotopy Cartesian, has trivial total fiber. And so how's that going to work out? Well, because you've got this kind of x1, 2 here, and exactly the same thing here, both with a rational sphere tagged with x1, 2 here, these two kind of cancel out. They don't make any difference. And similarly, you've got a rational -1 sphere tagged with x0, 1, and the same thing down here. So this and this kind of cancel out. They don't make any difference. So what's left? You've got this -3 sphere tagged with x0, 2, and a -1 sphere here tagged with x1, 2. But you're taking a homotopy inverse limit, right? How does that work? I mean, here, if you take a homotopy inverse limit, you've got a homotopy pullback of a 0 and a 0 mapping to an s minus 3. But when you do this kind of business, you take 0 and 0 mapping to x, and you take the homotopy pullback of that. That just gives you an extra looping or an extra desuspension. So this s hat minus 3 here becomes an s hat minus 4 when you pull back here. And similarly, this guy here, you take the homotopy pullback of a 0 and a 0 mapping into a s hat 1 minus 1, that gets shifts to a minus 2. So you end up here, like I say, this thing shifting down to a minus 4, and this thing here shifting down to a minus 2. So that's what you get as the first graded piece. And then the second graded piece, again, I'll say x02 gets mapped to 0 under this map here. So this product x02, x12 gets mapped to 0 also. So basically, you're just kind of picking up these two things. And so, as we said here, because we're taking a 0 and a 0 mapping into this s minus 4, you take the homotopy pullback, you get an s minus 5. And then similarly here, but this is kind of the very bottom right vertex of the cube. You're kind of taking a cube where you've got zeros mapping in from 3 directions, and you form the homotopy pullback. That gives you a double shift. Okay, so you get so this s at 0 minus 2 gets shifted to s 0 at minus 4. So that's our associated graded for this thing here. You've got 3 stages. You've got at each stage you've got various different kn local spheres. 5 of them in total. Various different chromatic height. So I did this for the E2 local case, and in general, it's going to work out similarly. The chromatic spinning conjecture implies you take this EM local sphere, then it's going to have a finite decreasing filtration, like the one we discussed here, associated graded, so a wedge of various km local spheres for different m, and everything that the precise details can be described combinatorically. I'll do that on the next slide. Multiplicative properties are unclear, at least for the moment. Should be tractable to kind of understand what the ring structure is like. With a bit more work, but I haven't got to that. Okay, so spell out conjecture at least what's going. So firstly, it works out like this. You've got a sequence like this. So we're looking at the associated gradient for the EN local sphere. And there's some stuff going on related to sequences like this, strictly increasing sequences, which end up at n. Any sequence like this, you get a map, which I'm going to call ZU. It's from K local sphere, the relevant height being the first term in the sequence, U0, and the dimension being twice the gap between the beginning and the end. This is mapping into the rth graded piece, where R is kind of the length of the sequence here. Rth graded piece of the EN local sphere. And we can kind of say, I don't know exactly how to describe this ZU, but it's kind of it is related to a different thing, which I'm going to call Z prime U. A bit difficult to spell out exactly what the relationship is, and somewhat conjectural, but I'll say something at least. Okay. So there's this alpha n. Fits into a fibration like this. So I've written it as a fibration, basically just to save space, but it's basically saying we've got a homotopy Cartesian square, Sn, Sn minus 1, Sn hat, and alpha ns. That's the same kind of chromatic fracture thing as we've been discussing previously. But then you've got a connecting map in this vibration, which I'm going to call delta n, from alpha ns to the En local sphere dimension, suspension of the En local sphere. Okay. Okay, so from this, well, I can take this delta j here. I can compose it with one of these guys xij that we are assuming comes from the chromatic splitting conjecture. And it's convenient for bookkeeping purposes just to suspend this map by 2j minus 1, and then then the grading behavior is kind of tidier. Get a map from the EI localization of the 2i sphere to the EJ localization of the 2j sphere, and this I'm going to call Z prime ij. And of course, these are sort of begging to be composed. And so you take a bunch of these, you've got a sequence like this, and then you get a bunch of these Z primes from the U0 localization of the 2U0 sphere, the U1 localization of the 2U1 sphere, and so on, all the way up to the 2UR localization of the UR sphere. And remember, UR is N, so this is the EN localization of the 2N sphere. And so that's kind of similar, you know, once we just move the 2N over to the left-hand side, that's kind of similar to what we've got over here. But this one so it's different because here you've got the KN localization instead of the EN localization, and then over here we've got the half graded piece. So it's a little bit some work to try and spell out what's the relation, what exactly the relation between this composite and this map here, but it's at least somehow related. Then yeah, each of these kind of ZUs is kind of gets multiplied by one of these sort of spectral exterior algebras we've been talking about. You get you get a bunch of variables that are indexed by the i's that sort of fit in the gap between uj minus 1 and uj. So, yeah, so you've got a bunch of these variables maybe, and they generate an exterior algebra, and this ZU can be multiplied by elements of that exterior algebra. And so that gives you a bunch of products of the ZUs times some of these x's. These kind of monomial things, they form a basis in the sort of evidence sense for this associated graded. Associated graded is going to be a wedge of Kn local spheres or Km local spheres, sort of indexed by this basis that we've got. Okay. And so that gives you this kind of associated graded for this Sn. And so from that, you get that kind of gives you the E1 term of a spectral sequence which converges to the homotopy of Sn, or similar ones which would converge to other kind of invariants, the Morava E-theory or K-theory of Sn or something. And again, as with the previous thing, I think it's tidier if we sort of reorganize the spectral sequence slightly so that the invariants of Sn itself appear on the E1 page, and then the spectral sequence converges to 0. But let's say we've got this is work in progress. I don't really understand what to say about the spectral sequence yet, but I think it's a very interesting spectral sequence that we should be looking at. So a few more things. Oh, not a little thing that we can say. Not any of these kind of spectra X. We can try and look at the Morava K-theory Euler characteristic. So assuming that the Morava K-theory of your X is finite dimensional over the Morava K-theory of a point, then you can just take the difference between the dimension of the even part, dimension of the odd part, and that's this kind of Euler characteristics additive on fiber sequences and so on. So that's kind of a useful thing to look at. Of course, it's not super useful because it's just zero really a lot of the time in these cases. But it's not quite always. Sometimes it's 1. Very occasionally, it's neither 0 nor 1. When I say it's a 0 or 1, sometimes we sort of can prove that unconditionally, or sometimes we have to assume the chromatic splitting conjecture and then we see that the Euler characteristic is 1. But there are also a few interesting consistency checks. I mean, sometimes you say, is this compatible with Euler characteristics? And you just sort of see it's kind of 0 equals 0 in a rather obvious way, and that's not very interesting. But with respect to the kind of thing that I had on the previous slide, where we've got this somewhat complicated filtration of Sn, then the kind of cancellation patterns are a bit more interesting, and it's not quite so obvious that everything's consistent with the Euler characteristics, but in fact it is. Some other questions. I just mentioned there's some stuff that worked out earlier with Nicola Bellemare. So we these functions that we call theta u. Okay, so you've got some subset u of the so u is a set of subsets of 0 up to n, and it's kind of closed upwards. So if a is in u and a prime is bigger than a, then a prime is also in u. So if you've got a set system like that, then you define theta ux to be the homotopy inverse limit of the corresponding phi A axes. So it kind of looks a bit harmless. There's a fair amount of foundational work needs to be done in order to kind of make sense of this, because these, of course, take the homotopy inverse limit. You need an actually commuting diagram. These phi A's as localizations. They're kind of defined by universal properties rather than really being strict functors on the node. So there's some foundational stuff to make sure that makes sense. But that can be done. If you look at the class of all these functors, theta u, well, they form a monoid. These possible u's, they form a monoid in a rather interesting and non-obvious way. And then this theta construction is monoidal. You've got two of these u. You've got a u and a v. Then we define a different set system called u star v, and then theta u, theta v is the same as theta u star v. So the class of functors that you get is closed under composition. It contains all the en localizations and kn localizations, and those in the composition also certain kind of homotopy limits. So this is a kind of rather nice system of functors to use if you're interested in any of this kind of story about iterated localization. So we believe that the chromatic splitting injector gives us splitting of all these theta u's, but there's more work to be done about it. Another thing that I think is important about the chromatic splitting injector, there's these spectra called Tn, so kind of which start with T0 is S and end with T infinity is BP, being used for a whole bunch of stuff in different areas of chromatic homotopy theory. Proof of the nilpotence theorem is essentially to do with these, and various approaches, telescope conjecture, are to do with these T's, and a bunch of other things. So of course, chromatic splitting injector is about what we do with applying these functors phi A and alpha A to T0. So you could also think about doing it over T infinity. Stuff about, and those are kind of very classical computations and localizations of BP. Kind of interesting answers, but well understood. And your generators XIM, they map to 0 over there. So it's an interesting story, but really a rather different story. But if you want to do alpha, you could think about applying these functions alpha k to Tn. Of course, the kind of most interesting part is going to be the transition as k sort of slightly less than n or equal to n, slightly bigger than n. There's also kind of a critical region, as it were, for the telescope conjecture. Would be very interesting to see what's going on. So again, I will stop there.
Thank you, Neil. Can we all unmute ourselves and give the speaker a round of applause, please? Okay, if you have any questions for Neil, please ask them now, either by unmuting yourself or by putting them in the chat. I'll wait to see.
Is filtration related to, or rather, how is Beaudry's counterexample interacting with the existence of this filtration in the conjecture?
Yeah, I've not checked that out. That would be, that would certainly be a good thing to check. I haven't done it.
Thank you, John. Do we have any more questions? Any questions, any comments? Hello, Jack.
Well, I once tried to chase down the Q mod Zs in the En localization of the sphere spectrum. There's a little note on the archive about it. And there are some kind of reasonable conjectural formulas you can write down, I think. They're not very complicated. The interesting thing, if there is anything interesting about them, is that they sort of look like the inverse of something sensible, or the reciprocal of something sensible. In the way that Cazul duals, when you work with Poincare series associated to Cazul duals, the Cazul dual of something often turns out, the Poincare series of the Cazul dual of something turns out to look like the reciprocal the Cazul dual of the other thing. This goes way back to early days of the spectral sequence and things like that. And I don't know if this is at all relevant to what they're doing, but I just wondered if there might be this monoid that you mentioned might have some Cazulish properties, but that's very speculative. I mean, I don't know what I'm talking about.
Yeah, I think there is certainly a bunch of interesting questions about duality. I mean, of course, yeah. So there's a bunch of stuff about Gross-Hopkins duality in K and local homotopy. But then we do this kind of transchromatic thing. You do the Kn local and then you En-1 localize. I don't know any kind of fragment of that duality story that persists when you do that. But it would be very interesting to look for. And again, I mean, I'll kind of, this is somewhat separate brand, but I think I think there's because here we're doing a bunch of this stuff with kind of spectral sequences, and one thing that I think is really missing is kind of any interface between duality phenomena and spectral sequences. Like if you look at the Morava K-theory of the classifying space of a finite group, right? You know that yeah, that's kind of automatically self-dual, right? But a lot of the time when people try to calculate Morava K-theory of classifying space of a finite group, you do it with some kind of spectral sequence or other. And the spectral sequence doesn't know anything about self-duality. And then you go away and you work really hard to calculate differentials and everything, and then miraculously, at the end of the day, you've got your duality back again. And it would be much better if there were kind of methods for dealing with these things that sort of propagated the duality automatically. And the only thing like that does work is kind of surgery, right? There's a whole, you got to calculate cohomology manifolds, then you can do surgical construction for manifolds, and they automatically give you manifolds, and then there's some kind of homological counterpart of the surgical constructions, which sort of automatically giving you Poincare duality also. And I think that's a really, I've been kind of trying to think of a good way to do that on and off for a long time, but I've never managed to make it work.
Thank you, Jack, for the question. Do we have any more questions for the speaker? I heard something.
That was a great talk.
Thank you.
Yeah, that was a great talk. Yeah.
Yeah, great fun.
Okay, it looks like we don't have any more questions, so let us thank the speaker again. So in all likelihood, we won't have a talk next week, but I think there will be a talk the week after that. I'll email everyone once I have the details. Okay, thank you all for coming.
Thank you. Bye-bye.
Bye.